Good morning, everyone. We'll continue this morning in chapter 6. Hopefully we'll come close to finishing chapter 6 today, if not completely finishing it, so we can spend some time on Friday reviewing ahead of midterm 3 next week. We're talking about quantum numbers and sort of trying to get to a description of where electrons might be located within multi-electron atoms. Last time we were talking about the principal quantum number n. N was the quantum number we were seeing in the Bohr model experiment. So n is a principal quantum number. It's related to size. N can be 1, 2, 3 on upward and whole numbers. L relates to the shape, and it takes on values of 0, 1, 2 on upward. And so this is going to tell us the type of shape we have. 0 will be S-shaped, 1 will be P-shaped, 2 will be D-shaped. We'll look back at the slide that shows us some more pictures of shape. If we go through 3, that's F-shaped orbitals. And then we'll see kind of like no lobes, a set of lobes for P-shaped. So if we're looking at, the number of lobes on some of the orbitals, we'll see like 0, 1, 2, 3, kind of reflective of the number that the L value is. But then the M sub L is going to tell us something important. It's going to tell us the projection of the orbital, but then also how many projections of the orbital there are. And so L can range from minus L to L, including 0, and all integers between. So if L, let's say for an orbital, let's say we have n equals 3, let's say L is equal to 2 for a particular orbital, then the M sub L could range from minus 2 to minus 1 to 0 to plus 1 to plus 2. And so that would be 1, 2, 3, 4, 5 different M sub L values. So we would have 5 different orbitals that could represent or could have that L equals 2 number when n is equal to 3. So we could have 5 orbitals within what we would call that 3D subshell. So we get 5 orbitals within the 3D subshell. Now, what the M sub L kind of tells us is how the 2 sets of lobes or the shape of the orbital, where it's projected in space. So it's going to tell us that we have 5 different projections of the orbital. So it's important, I think, to see M sub L is telling you the range that you have, and then how many of them tells you how many orbitals can share that combination of N and L. There's a lot that goes on in these couple sections that get into quantum numbers, their range of values, and then how they relate to orbitals. So there's a lot that kind of simultaneously we have to understand. So there'll be a few slides that we look at where we see that we can have one S orbital, or excuse me, just one general S orbital within any given S subshell. We can have 3 p orbitals within any p orbital subshell, 5 d orbitals, 7 f orbitals. If you look at our periodic table, we kind of have an S block of 2 elements because we can get 2 electrons per orbital. So we have like an S block of 2, a p block of 6, a d block of 10, and then across the bottom, the lanthanide and actinide series, 14 across. I'm kind of showing you that we have like an F block. So you can kind of start to see how the periodic table is coming together. Let's take a look again at this slide. We quickly, at the very end of class, looked at this slide. The n value is looking at size. So this is just showing you the n value increasing leads to a larger orbital. So the n value is related to size. So 1s versus 2s versus 3s, those are just increasing orbital sizes. And then the next thing that we see are what the p orbitals look like. So these are the combination when L is equal to 1. The S shape is where L is equal to 0. So the P-shaped orbital, it's when we start putting together a periodic table, and we started thinking about that last time too, when we're thinking of like hydrogen having 1 electron in an S orbital, helium having a second electron, and then lithium and beryllium are simply putting their next electrons into S orbitals as well. So if you're just thinking of what these atoms might look like for hydrogen versus helium versus lithium versus beryllium, they're just filling electrons into these spherical type orbitals. And then we're putting 1 electron spinning, like if you imagine clockwise, and the other one spinning counterclockwise. If we're thinking of like diagrams, we can write 1s and 2s either horizontally like this, or sometimes we write it vertically like this. The vertical combination is showing you that you have an increasing energy. You can see that in either direction. So the 2s orbital is higher in energy than the 1s. So you can either write it left to right or top to bottom, kind of showing 1s, lower in energy than the 2s. But the idea is you have one electron spin one direction, the other spin paired. And then if I'm picturing electrons in an orbital, if you notice, it might look like I'm writing the electrons in the same spin, but it's really kind of showing one's clockwise, the other's counterclockwise. So that would be the opposing spins. So then if you imagine that gets us through the first 4 elements, then the next question would be, well, if you're the element boron, and you can do whatever you want to do, you can put your electrons into whatever orbital you want to put them into. The question would probably be, do we just keep packing into s orbitals, or do we find some other type of orbital? And boron makes use of a new type of orbital. It makes use of that p-type orbital that fills an electron into a shape like this, where our shading looks maybe like one of these orbitals here. Maybe it looks like this orbital here. Puts an electron into that p orbital. Carbon uses another p orbital. Nitrogen uses the third. So we start filling into these orbitals here in 3 dimensions as we go across the boron, carbon, nitrogen. Think of the electrons. The electrons are all the same charge. They're all negative. They repel each other. So the electrons want to get away from each other, but then they're being pulled into the positive charge of the nucleus. So there's this give and take of the electrons don't like each other, but they like the positive charge. The p orbitals puts the electrons relatively closer together, but then as the atoms grow larger, the p orbitals are bigger. So you can sort of picture, why did we not get a p group after helium? Why did we not go hydrogen, helium, and then have 6 elements filling into like a 1p subshell? Well, the answer must be that those electrons would be too close together. They would repel too much, so that subshell didn't exist. So that's why our L cap was at n-1. So when we had the 1s, or n equals 1, we can only have L equals 0. We could not have L equals 1. So I think the physical explanation would be, if we had p orbitals that were smaller, those electrons would just be butting into each other and repelling, and therefore turn out not to exist. But then we can have the 3 sets of p orbitals, so we get 6 elements across the periodic table, and then eventually we get across a whole other group. So we get across the 3s, the 3p, then we start filling into the 4s, like potassium and calcium. This is slightly getting ahead of ourselves. We'll see a couple slides that kind of get us through the first 18 elements. But once we get to potassium and calcium, filling back into like an s block, we then start filling into a d block. And the d orbitals have a second set of lobes here. So these are L2 combination. And so our L equals 2 combination look like 2 sets of lobes, or really what they have are what we call 2 nodal planes. So they have 2 nodal planes that bisect the lobes. And then the weird like donut shaped one has like 2 planes that cut through the ring. So we have 4 kind of double lobes, and then a 5th orbital that has a ring around it. The shading is showing you where the probability of finding electrons is higher. So where the shading is where you expect to find electrons more probably within these diagrams. If you imagine overlaying the p orbitals, you can kind of see the problem here of having d orbitals for relatively small elements is that they're also putting electrons really close to the p orbitals. So we're not really going to be able to have a set of d orbitals until we expand into larger elements. That's why we don't see d orbitals popping up until we get past kind of or into that 3rd row. And then the f orbitals, these aren't even in our textbook, so this is just a picture from the internet. These are the combination of orbitals when L is equal to 3, and they pretty much look exactly, I think, like you would expect for the most part of having 3 sets of lobes. So they kind of just look like 1 set for P, 2 set of lobes for D, and then 3 sets of lobes for F. And then you have some of these really weird looking combinations where you have a double set of rings. I don't expect us to really interpret too much of the shape of the f orbitals, just that they kind of continue this kind of picture of packing electrons between the orbitals. So think if you have p orbitals that are in this plane, the d orbitals want to use the plane in between. So if you notice, the p orbitals generally on the axes, most of the d orbitals are either bisecting the axes or they're like expanding beyond where the p orbital would be. So like if you look at this orbital here, the p orbitals would be smaller and the d is going to occupy the space more prominently beyond where the p orbitals are. Because remember, the electrons repel, they want to get away from each other, and they don't want to be in the same space as each other. And so we're just trying to carve out space around atoms for the electrons to distribute into, but also we're trying to make sense of what elements really do and how they physically are able to use the space that surrounds them. So this is kind of a picture of the L equals 0 through L equals 3. So the L value is telling us the shape. But then if you notice the m sub l projection, like the -1, 0, +1 combination showing you should have 3p orbitals, the -2, -1, 0, 1, 2 for the d, you get 5d orbitals. And then L is equal to 3, -3, -2, -1, 0, +1, +2, +3. So you should have 7 f orbitals, and there's 7 pictures here. So we get the proper number of orbitals within each kind of subshell set here when we take a look at the picture of the orbitals. Okay, so let's then think about the m sub s quantum number. The m sub s is just the one that says each orbital. An orbital is defined by an n, l, and m sub l. So if you know those 3 combinations, those are referring to a particular orbital. An n and l combination refer to a subshell. So the sort of idea would be, like if you have, say, n equals 3, then the L could range from being 0 to 1 or to 2. And so these refer to the 3s subshell, the 3p subshell, and then the 3d subshell. All of them together refer to the n equals 3 shell. So the n value tells you the shell, n and l together a subshell, and then a specific n-l m sub l combination that's allowed would refer to an orbital. And then an electron would then have to have an m sub s quantum number where it's equal to plus or minus 1/2. Think of the idea being you're either plus 1/2 spin or minus 1/2 spin. You can either spin one direction around a magnetic field or the opposite direction around a magnetic field. When we write a configuration, hydrogen's a really easy example because it has 1 electron. So hydrogen, we can write it this way or we can write it that way. It's actually legal to write the spin either up or down because we're not really ever defining the spin of the electron absent a magnetic field anyways. So it's kind of a hard to understand concept that if we write spin up, it doesn't necessarily mean spin plus 1/2. Spin plus 1/2 just means it spins in parallel with the field. The spin minus 1/2 means it spins opposite of the field. So we can write either combination, but then we tend to write the combination this way. So like we tend to write, whenever we have an unpaired electron, we usually write it spin upward, but we could write it downward. There's nothing wrong with writing the spin down. So if we're writing the sort of configuration for helium, where we know it has 2 electrons, spin up or down, we could theoretically write it spin down, spin up. We just tend not to write it that way. So you could write it either way. But conventionally, we usually go up, down, just to give you an idea of how we're writing these configurations. But the thing that we can't do is we can't do this. That would be wrong. We can't do down, down. That would be wrong, because that would be showing the spin of the electrons having the same spin as each other. That would be violating that Pauli exclusion principle. That would show us the electrons would have the same set of 4 quantum numbers, which they can't have. So each electron in an atom has to have a unique set of 4 quantum numbers. Now let's kind of go through the first few shells. So we have the n equals 1 shell. That's comprised of just the one possible value of L of 0. So that's just the 1s subshell. That's hydrogen and helium. So that's pretty straightforward. We go through the n equals 2 shell. And so then we have the 2s subshell and the 2p subshell for L of 0, L of 1. We can't get to an L of 2, again, because the max L is n minus 1. So obviously n is 2, the highest L can be is 1. And so then we have the range of m sub L's of just 0 for the 2s, and then we get the 3 orbitals for the 2p. That's showing us that we have 3 2p orbitals within that subshell, but only 1 2s. And that's fitting into our periodic table really well. So this would be helping us describe hydrogen and helium, lithium and beryllium. And then with the 2p combination here, this will be describing the boron to neon using those subshells. Then we go through n equals 3. The only kind of peculiar thing is when we get to the D, we'll see that we have to skip and fill an S first. But we go 3s, that's just 1 orbital. The 3p subshell, we get 3 3p orbitals. And then the 3d would, of course, have 5 from the range of 5 m sub L numbers. So we have, within the entire n equals 3 shell, we have 9 possible orbitals. So then we could fill 2 electrons into each, so that would give us 18 total electrons that can fill into the n=3 shell. And then in terms of the elements that last fill electrons into the 3s, so the last electrons using the 3s, that would be sodium, magnesium. And then we're going to fill into the 3p when we go across aluminum. So it's like aluminum's configuration. And we can start to write configurations. It's actually write one for aluminum. So aluminum, we can write it. It fills electrons into a 1s2. So 2 electrons into that 1s subshell. Then it goes 2 electrons into the 2s. Then 6 into the 2p. The 3s gets its 2. And then finally a 3p1. And if you get stuck on configurations, it's really the periodic table. It's like 1s2, lithium, beryllium, 2s2, boron to neon, 2p6 across. Then we go 3s2, and then aluminum's a 3p1, silicon a 3p2, phosphorus a 3p3. So we're just filling into that 3p subshell with those last electrons. And so we're last filling in here across the aluminum to argon, range on the periodic table. Then our 3D subshell, we got to skip 2, but the 3D is going to be the 10 across group. It's scandium to zinc. Now let's look at the range of the n=4 shell and then kind of come back to the order in which we fill orbitals into. Can be complicated, but the periodic table is nature figuring this out for us, or us trying to figure nature out through the set of quantum numbers too. So nature and these quantum numbers have to go hand in hand. So we go 4s, 1 subshell, 4p, 3, 5d, or excuse me, the 4d for 5 orbitals, and then the 4f for 7 orbitals. And so if we look at our periodic table, we would see the next s block, the next 2 elements on this block of the table are potassium and calcium. The 4p would be the next p block group. So we look at our p block, the group of 6, so that's gallium to krypton. Now the 4d are in our d block. We're back into the transition metals. That's yttrium across the cadmium. Then the 4f are way later. The 4f aren't down until we get into the next block that come down here. This periodic table is kind of silly. Not a big, like they put lanthanum and actinum in like the D block area. They should be down below. So La and AC should really be in the block below. And then the Lu and the Lr should be where La and AC are. The periodic table you get on the test is better than this one here in the room. But so anyways, we get 14 across, and it's going to go lanthanum on across to, let's count this out, 2. So it should be lanthanum is 57, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. I already lost count. But it should be across to Yb, ytterbium. Okay, so, but the key is, we're going to have to like get a little bit into the periodic table to see why it is so late in terms of element count that we finally start filling into the 4F. One explanation could be that you just continue the periodic table. Like if you go after krypton, then you got to get to the S block again. So you got to fill into the 5S because that would come next. And then you got to get across that 4D, then you got to get across the 5P. There's a slide that'll show this, so let me kind of hold off on showing you some of the bigger elements until we get to that particular slide. Okay, so let's ask a couple generic questions. What's the most number of electrons that could occupy the N= shell within like one particular atom? So think about that for a couple minutes, or maybe a minute, probably won't take you that long. Feel free to compare with your neighbor. If you were coming up with 18, that would be the right answer because the n equals 3 shell would be the 3s, the 3p, and the 3d subshells because that's our range of allowed L values. And so when n is 3, the highest L can be is 2. And so then we get the range of m sub L's tell us 1 3s orbital, 3 3p orbitals, 5 3d orbitals. And so that's 9 total orbitals, 2 electrons each. If we are picturing the most electrons that can go into this subshell, we haven't talked about this rule yet that I'm using here in that we're going to try to maximize spin when we're writing configurations. We'll see that rule in a minute. But we can get 2 electrons per orbital, so that gets us to 18 total. Now, the only confusing part here is you might have been confused and said, well, the third row of the periodic table only has 10 elements. Maybe you were thinking the answer was 10 because the third row only has 10 elements in it. There's a difference between the n equals 3 shell versus the n equals 3 row because it's not until the fourth row that we write in the 3D block elements that are using the 3D subshell. So the rows don't match up with the shell count. Let's take a look at another question. For an electron within a 3p subshell, what's its range of m sub L values? So if we know an element's using the 3p subshell, the m sub L could be any range within -1 to 0 to 1, because the L value, of course, is 1. So the range of m sub L has to go -1, 0, 1. Now, sometimes the confusing part here is going back to n is 3 for this orbital, but for this particular orbital, the L is 1. It's possible that there could be a different electron that would have an L of 2 that would be in a different subshell. So you may be confused here thinking, well, but can't L be 2? Well, if it did, that would be the 3D subshell, not a 3P subshell. So if you were thinking maybe B looked like a good answer, B is not the right answer because that would be the range for a 3D subshell. Even though that's possible within an N of 3, that's not possible within the 3P subshell. So like if we're looking at the aluminum, if we go back to the aluminum configuration where if you remember it ended with a 3P1 configuration. So if we were looking at aluminum and saying aluminum, we know it has 1 electron here. So another question might be, is that m sub L -1, 0, or 1? We don't know. It's not defined. So we don't know what the m sub L is. It just could be -1, 0, or 1 in just one of those numbers. Same thing with the idea with hydrogen. It's like when we're thinking of hydrogen, is that spin +1/2 or -1/2? It's kind of like undefined. If we write a configuration for argon, where argon would completely fill this subshell, then you could say for argon, it has 2 electrons with an m sub L of -1 within the 3p subshell. So you can say, well, for sure, one of those is -1, one of them is 0, one of them is +1, and each one of those combinations would have 2 electrons. So there's a lot of like word problems we'll ask about quantum numbers that just kind of get at the rules for the quantum numbers and then tandemly how elements use the subshells and fill electrons into the subshell. This topic here is getting into then what the orbitals look like in terms of probability distributions, looking at them a little bit more carefully. So this diagram here is showing us that a 1s subshell, this is if you imagine the nucleus of the atom, and one of the ways we show the configuration is like with the sphere, but if you then think from the center of the atom outward, where's the probability of finding the electron? And you see that the probability of finding a 1s electron is pretty close to the nucleus within a 1s subshell. So if you think from the nucleus being at 0 on outward for the atom, where's the highest probability of finding the electron? It's sort of near the nucleus. So it's like if you could picture the shading of the sphere, it's like it would be a little bit lighter, then darker in the middle, and then lighter as you go out. And then you can project that within what we call a radial distribution diagram. And one of the keys is if you look at that radial distribution diagram for a 2s subshell, it turns out to have something interesting. It turns out to have a node within it. It has a region of no probability. So if you could look within a sphere would look like it would have a shading here, and then it would have a shading here, and then there'd be like nothing, there'd be like a 0 probability region in between the spheres. If you look at a 3s subshell, it has 2 of these nodes. We just have 1 node within the 2s. We have 0 nodes within the 1s. We call these nodes specifically radial nodes because they're nodes along the radial trajectory or the radial path of the atom. So these would be called radial nodes. And these are different than the type of nodes we might call within like a p orbital. So a p orbital has a nodal plane that's a little bit of a different idea than these radial nodes. So the nodal plane within like p orbitals, where the d orbitals have 2 of them, the f orbitals have 3 of them. These are either planar nodes or axial nodes, sometimes they're called, but these are more like planar nodes. So we get, and to be honest, I don't know why these, sometimes you see old exam questions that ask, how many nodes does a particular orbital have? Usually we ask radial nodes along the radius of the atom, where it's just the 2s has the 1, the 3s has 2. If we ask about a 5s, it would have 4 nodes in terms of these radial nodes. And it has 0 of those nodes through the center of the atom. So none of those nodes go through directly the center of the atom. The center of the atom nodes is the L value. I think there's a picture, yeah, this picture here, which I'm gonna have to zoom in so we can kind of try to make out some of the differences for some of the bigger orbitals. If you look at the p orbital, the 2 p orbitals, the first time we can have a p orbital is when n is equal to 2, and there's no radial nodes here. So if you notice, the 2p orbital has 0 radial nodes. Of course, it's characterized by having that one node through the actual center of the atom. It's the p orbital has, of course, still the node through the center of the atom. But then if you look at the 3p here, so the 3p is this curve here. It's kind of hard to follow the curve. It's this curve here. And so the 3p, though, should end up having the 1 radial node. So like the first time you can have a particular subshell, there should be 0 radial nodes. So if we look within the 3D, let me change colors, the 3D is this curve here, and it has 0 radial nodes because that's the first D subshell. Not shown here is a 4D, but a 4D would have 1 of those radial nodes. But of course, D subshells are still characterized by that L of 2, having 2 nodes through the center of the atom, so 2 of those axial or planar nodes. You can pick up the same thing that we were seeing within the S, that the S has the 1 node, the 3S, hard to picture, but it has the 2 nodes here. Now, the real picture here will come up in chapter 7 again, why it's important to kind of note that even as the n goes up, as you go from n equals 1 to 2 to 3, that there's still some probability, even for n equals 3, of that electron being relatively close to the nucleus. That'll be important for us to understand later, that even though as the n goes up, there's still some probability of those electrons fighting for space relatively close to the nucleus. So it's not as if the 1s electron, which should sit right on top of the nucleus. It's not as if it just wins the space and kicks all the other electrons out all the time. There's still some other electrons that will kind of sneak into the space, have some probability relatively close to the nucleus. And that's something that will help us to understand on some aspects in chapter 7 when we get into the next chapter. Okay, so the concept of radial nodes is just from the first time you can have a particular subshell, 0 radial nodes, and then just 1 additional one for each time the n value goes up. So the questions on this topic are usually pretty straightforward because sometimes it'll show you a picture, sometimes it'll just ask a question like this: how many radial nodes does a radial probability distribution function show for a 6s orbital? And so it should just be 6s, the 1s would have 0, 2s 1, so this should have 5. So you should get 5 of those radial nodes. How many radial nodes does a radial distribution function for a 2p contain? Should be 0, because that's the first time we can have that subshell. So it should be 0 for the first question. And then the planar nodes, this is the L value, so it has 1 planar node. And so just trying to make sure that we see that you still have the plane through the center of the atom where there's a point of 0 probability. So any point where there's no probability or there's no shading is a point of 0 probability. So let's talk more about writing the orbital diagrams. So we've already been writing some of these. So of course, hydrogen, we can go up or down, but conventionally up. Helium, up, down, or down, up, but again, conventionally usually up, down. Lithium, like hydrogen, will have one net up electron. So we go 1s with 2 in terms of the configuration, be a 1s2, a 2s1, and showing the electrons going in. And again, this one here could be written up or down, but conventionally we tend to write it up. The direction of the arrow represents the relative spin of the electron. So we just can't write like the 2 in lithium. We can't write these two both up or both down. It has to be one up, one down. As long as one's up, one's down, we're good. The net number of unpaired electrons, sometimes we count that. So we have 1 unpaired electron. We have 0 unpaired electrons within helium. So both the electrons are spin paired. We have 1 unpaired electron within lithium. So we'll be noting the unpaired count a lot because sometimes it's a question we'll ask. Consider the configuration for something like nitrogen. How many unpaired electrons does it have? If you have the wrong configuration, usually you'll have the wrong electron unpaired count. So usually we'll ask and track the number of unpaired electrons. So we'll track that as we go. So let's continue across lithium, beryllium, across the next few elements. And then we'll pick up this Hund's rule. So when filling into what are called degenerate orbitals, degenerate orbitals are orbitals that are equal in energy. So when we're looking at our orbital set for like 1s, the 2s being higher in energy, the 2p come next. So these are degenerate. Orbitals. Degenerate's an interesting word, has a lot of different uses in the real world, but in the chemistry sense, it just means equal energy. So orbitals of equal energy, then the way we're going to think about how we use space, I think makes a lot of physical sense on why we're going to do this. If we picture filling electrons in to the 1s, 2 electrons, the 2s, 2 electrons, and we fill our first electron into a 2p subshell, so we've kind of done this, and then we've gone across boron, which only fills into 1, so boron was pretty easy. It would look like that configuration. When we're at carbon, we're going to put a second electron into the mix. Where do you think you want to put an electron if you're carbon? Do you want to put another electron into this space here, so we'd have 2 electrons in the same space, or do you think you want to maximize the use of space and use a different orbital? So you end up using a different orbital. So you put an electron into a different orbital, and that gets the electrons further away from each other. So Hund's rule is really just disperse the electrons to be as far away as they can, and then generally we're going to maximize the spin. So instead of going up, down in different orbitals, we're going to pair the spins together so that they spin in the same direction. And then if we go to nitrogen, we just continue having use a third orbital in 3 dimensions. We'd have one on one axis, one on another, one on the third axis. And then we use all 3 orbitals with 1 electron each. And then once we get then across to oxygen, fluorine, and neon, oxygen's going to have to spin pair. So if we go to oxygen, we got to spin pair. If we're fluorine, we have to spin pair. Neon, we have to spin pair because we have nowhere else to put the electrons. So then we start then filling and completing the shells for, filling those orbitals for oxygen, fluorine, and neon. So the unpaired count, of course, here would look like this. The unpaired electron count would just be 1, 2, and 3 for boron to carbon to nitrogen. If you had a configuration for nitrogen, if you said, well, what's wrong with a 2s2 and then writing something like this, why would that be wrong? That would be wrong because it violates Hund's rule. That would be wrong physically because it would put 2 electrons closer together where they're going to experience a greater repulsion. This is just what we would call a higher energy configuration. The most stable, the ground state configuration should be the one that looks like this, where we put the electrons spin paired into the same direction. If we then show a configuration that says, well, why don't we really maximize spin? Like, if you're saying maximize spin, what's wrong with this then? Doesn't that maximize spin? Well, maximizes spin at the expense of the Pauli exclusion principle. So the Pauli exclusion principle prevents us from maximizing spin within the same subshell. So we have to follow Pauli exclusion still and only put 1 electron up, the other has to be down within a particular orbital. And so neon caps off 0 unpaired electrons for neon, completely filled with 3 or excuse me, the 2p subshell. And you can now probably see why the noble gases are so stable, because they're the elements that cap off a particular subshell, and they cap off and totally fill that P subshell. And what we're going to see also next chapter is that the noble gases take a tremendous amount of energy to ionize either way. So it takes too much energy to make a cation out of a noble gas, and takes way too much energy to make an anion out of the noble gases. So they just stay put as is, and they turn out to be stable monoatomic gases at room temperature, because they have that stable configuration, and they're just happy as can be having that count of electrons where they don't have to exchange electrons with their neighbors in order to gain some kind of stability. Sodium, of course, has that one extra electron that we're going to see, or we've seen before, that it can lose that 3s electron, go to sodium plus. You can see that it's really close to having that stable configuration of the noble gas of neon by losing the 3s electron. Next chapter, in chapter 8, will also get us into the idea that once you make sodium plus, it can give the electron to chlorine minus, and then they can have that electrostatic attractive force. So it's kind of the consequence of why certain compounds form is usually not because of one atom's property, but it's the property of the one atom with the second atom's property, and then with the resulting attractive force. So it's like the whole picture of energy. It's kind of like the chapter 5 picture of bond strengths. It's not just about how weak or strong a particular bond is, it's how weak or strong that bond is compared to what the new bonds are going to be in the product side. So the reason why any chemical event takes place is usually the result of the properties of multiple substances, and then the aftermath once change starts to occur. But here in this chapter, we're just trying to get the configuration. So we're just trying to see that sodium would be a 1s2, 2s2, 2p6, 3s1. You can get that combination of subshells just by following the periodic table. This diagram here shows it too, but again, like if you follow the periodic table, you get the same order. So like if you're following the periodic table, hydrogen, helium, lithium, beryllium, boron through neon, sodium, magnesium, aluminum through argon, potassium and calcium, and then scandium across to zinc. And then finally, the 4p would be the next group of elements, gallium on across to krypton. So the order of those energies doesn't even have to be memorized. It's not like you have to commit this picture to memory. What you have to do is say, whatever this picture is had to match that picture. Because if the picture on our screen was something different, then the periodic table would have been something different. They have to make sense aligned together. In terms of the word degenerate, so what orbitals are degenerate? The orbitals that share a subshell are equal in energy for multi-electron atoms. Interestingly, if you look at hydrogen, if you look at just the H atom, then the 2p subshell is actually degenerate. The entire n equals 2 shell will be degenerate if you had just a single electron. So for an H atom, if you notice that when we were looking at the transitions of H, there was no difference for if you were going to the S or the P or the D. It's because they're equal when you have one electron. As soon as you have 2 or more electrons, all of a sudden the subshells take on their new energies and are degenerate only within the subshell. So the 2p subshells are degenerate within each other, the 3p's are degenerate, the 3d's are degenerate, the 4p's are all degenerate. So the orbitals that share a subshell together are degenerate with each other, and then that's it. They're only degenerate with each other there. So when we're filling into a d subshell, we can get 5 electrons spin paired into the same direction before we have to start spin pairing. This might jump ahead a little bit, but if we're looking at the configuration, manganese right in the middle of the D block, manganese in its configuration, if we're writing it, would be, and there's 2 ways we can write this. We can write it from scratch, like a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. That's nice to be able to write, but we can also go to the nearest noble gas. We could say the nearest noble gas preceding manganese would be argon. So the configuration of argon, that's 18 electrons here. And the 18 electrons there would be the 1s2, 2s2, 2p6, 3s2, 3p6 combination, and then followed by the 4s2, and then followed by the 3d5. Now, how do I get the 5 count? Well, we can just count across. So we can just go 4s2, and then 1, 2, 3, 4, 5 across into the D block to get the count of 5. Manganese should have the proper number of electrons shown. Manganese is element number 25. So we should have 18 plus 2 plus 5, 25 electrons shown within our configuration. So there's a lot of ways you can check your configuration. The electron should add up to the total number the element has. We're not even tracking ions in this chapter. Ion configurations are in the next chapter. So we're only looking at the configurations of neutral charged atoms. So just where the electron counts based on the proton count, based on the atomic number. And then in terms of the configuration diagram, if we're horizontal, we just write it like this. So we don't have to write vertically on a test or on paper because it might take too much space. We go 2 electrons in a 4s, lower energy than the higher energy D combination, 5 spin paired. So we'd have 5 unpaired electrons. All of those D would be unpaired. If we then go to iron, iron would just be the next element, argon, 4s2, 3d6. Then we'd have to spin pairs. So the 1, 2, 3, 4, 5 combination for the 4s and the 3d, we're just like 2 spin paired, and then 1, 2, 3, 4, 5, spin pairing one of them. So we'd have 4 unpaired for iron within its most stable electron configuration. Now, if you write a different configuration, like if you go back to the nitrogen picture where we spin paired, remember that example where it ended up having just 1 unpaired? We call that like an excited state configuration. So there can be configurations that are legal that atoms could have, but we're trying to get to the ground state lowest energy combination here within this chapter. Titanium, kind of like manganese, same basic idea. What's its ground state configuration? Let's go the entire configuration. Titanium's just the second across the D block. So if we're going from scratch, 1s2, 2s2, just follow the periodic table if you get stuck. 2p6, 3s2, 3p6, 4s2, and then we go back into the 3D. So why 3D and not 4D here? Well, one reason is that the first time there can be a D is when n is 3, and then we're just not filling into that block until the 4th row. So if you think, okay, how do we go from 4 to 3? It's just based on the quantum numbers. It's like the first time we can have the combination of L2 is when we have an n equals 3. So we have to fill the 3D subshell before we get to the 4D. So the 4D is not until the next row. And then in terms of unpaired electrons, we're just, again, kind of the same picture as before, 4s2, and then 3d2. So we should have 2 unpaired electrons. Now the valence count's an interesting question, or it's an interesting topic. The valence count are the electrons in the outermost shell. So what is a valence electron? But we also have to add any electrons in a lower unfilled subshell. So there's a lot going on there. So let's go smaller first. Let's go to carbon. Carbon's a 1s2, 2s2, 2p2. So the outermost shell is the n equals 2 shell for carbon. And so that would be these 4 electrons. So carbon should have 4 valence electrons. So the valence count are the electrons in the highest shell that the element has. And so then we're not counting the 1s. We call the 1s a core electron. So the electrons that aren't part of the valence are the core. The valence electrons are going to be the ones that are most important for bonding. They're going to be the ones that overlap with other valence electrons, that participate in gaining and losing those electrons. So the valence electrons, the outermost electrons. But now when we look at titanium, where it's filling into like tandemly the n equals 4 and the n equals 3 shell, how do we consider where we have like 2 shells that are kind of actively being filled? Well, the highest shell is still 4. So we're going to count those 2 into the valence count. So we get those 2 electrons here for sure, but then we're going to add these 2 electrons here as well. So we're going to get 4 valence electrons for titanium. So if we have an unfilled lower end subshell, like the 3D, where it's not completely filled, then we count those electrons towards the valence count. We don't do a lot of questions on exams asking about valence electrons because it's not that great of a question, but it's an important topic as we get into like Lewis structures in chapter 8, where we need to come up with a valence count. And often we're not doing valence counts for transition metals. And there's some really oddities, like if you look at like nickel would have a 4s2 3d8 configuration. And it would have 10 valence electrons. So the valence count would be all the way at 10. Does nickel really have 10 electrons that are important in its bonding? I don't know. But like, so in terms of the valence count, I would say it has 10 to answer the question correctly. But the chemistry of transition metals, of F-block metals, are going to be really complicated. So valence count the outermost shell plus anything in a lower subshell that's unfilled. We can determine the element from a configuration. If I give you a configuration, and it's a neutral atom, right? Because everything here in chapter 6 is for a neutral atom. Which atom? It would have to be uncharged. If we're an ion, I would have said ion. But then, like I said, we're not getting into ion configurations until chapter 7. But which atom neutral has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6? Well, we wrote it earlier, so you probably remember that would be iron. But if we're not sure, we're just adding all those electrons up. This is argon, that's the 18, plus 2, plus 6. So we're looking for element number 26. So if you didn't remember the configuration, because since we had just done this one, if you're trying to do this from scratch, just add up all the electrons. They add up to 26 electrons, so it should be the 26th element of iron. So what about getting all the way to tin? Tin is getting all the way through the next row of the periodic table. So let's see if we can get there. If we get to krypton, that's filling into the 4p. So let's start with krypton in terms of our configuration. So the configuration of krypton is 36 electrons across krypton. So 1s2, 2s2, all the way to the 4p6. And then after that, we would have to be filling into the 5s2. Now, if you forget if it's 5, we'll just go hydrogen's 1s, lithium's 2s, sodium's 3s, potassium's 4s. We're now filling across into the 5s2. We've already filled the 3d, so we go to the 4d, 10 across to get the whole way across. So that's getting all the way across from yttrium across the cadmium. Tin's element 50, so we're just 2 more. So we're at the 5p2. And again, if you're not sure, is this 6p, is it 4p? How do I know that's 5p? We'll just go boron's filling into the 2p, aluminum 3p, gallium 4p, indium 10 into the 5p. So it'd be a 5p. In terms of a diagram, it would look like this. 5s2, and then 5p, write these. So 5s2, and then 5p2. And we got a spin pair, the 2p, still follow Hund's rule. So we have 2 unpaired electrons. Our valence diagram would be this here, because we show the valence electrons in the valence electron diagram. So we have the 2 unpaired electrons, and then all 4 of those electrons shown are valence electrons. The entire group of carbon has 4 valence electrons, because they all will have completely filled d subshells. The only shell that's the highest would be the end shell that we're filling into. So carbon has 4, silicon 4, germanium 4, tin 4, lead 4. So the entire group of what we would call the main group, so like lithium, sodium, potassium all have 1, the alkaline have 2, the boron group 3. So you could look at the halogen group, fluorine, chlorine, bromine, iodine, they all share 7 valence electrons without even needing to check anything. So like if you're in the F, Cl, Br, once you get the fluorine, see it has 7 valence electrons, then you know the whole group has 7 valence electrons. So there's some group trends that you can pick up with valence electrons. This was the diagram I was referring to earlier that can help us try to keep track of the periodic table. This is kind of the thought I was using to come up with the idea that hydrogen's 1s, lithium's 2s, sodium downward, carbon, in terms of boron, aluminum, gallium filling in here. So if we're like looking at the configuration of, any particular element, say it's here, you know you got to get through all the configurations to that point to get to here. So we got to go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So we're just, let me go laser pointer. So we're just filling in this direction here across our periodic table. The F block here, this periodic table is really a much more better way to show the periodic table. We would have written the periodic table this way, just have to be too wide. So the F block is only shown down below the periodic table to simply fill the table into a space that we can print onto a smaller piece of paper. We should really wedge these elements in, and where do they get wedged in? It's not until the 6th row. So the 6th row is where we see cesium, barium, then lanthanum across the F block. So we go into the 6s2, then we finally fill the 4f. Why 4? Well, the first time we can have an L of 3, that's what F is when n is equal to 4. So the first F block is 4f, the second F block would be 5f, and as I mentioned earlier, once you get to this element here that's oganescent, all at the end of the 7p block to this point, that's the last element that's been discovered in terms of pure atomic number. Physicists are trying to discover into the 8th row. Probably won't be much utility in any of those elements. Maybe there will, I don't know. But they're trying to discover elements into the 8th row, but none have yet been discovered. So the last element that we fill into is here, it's oganescent. And our periodic table needs to be updated because oganescent was only discovered in the last like 10 years. Okay, so let's come back to that. Next time, let's come back to this next time. Let's just end here with our quiz for today. The key word for today is uranium, and I guess that'll be the clue. Next time, let's look at uranium's configuration. We'll consider that at the start of class next week and wrap up with chapter 6, get into some review. As soon as you wrap up the quiz, feel free to take off, and I'll see you on Friday.